is Charwan Choi. Last time I made a presentation about echo cancellation, sound source localization, and speaker diarization. Today I'll be making a presentation about how I implemented these and how I plan on improving them in the future. Let's start with echo cancellation. First, the situation we need echo cancellation is when we have a speaker and a microphone in the same vicinity, and the sound from the speaker can go into the microphone, so we want to filter out the sound from the speaker from the signals going to the other side, and we use adaptive filters for that. There are many types of adaptive filters. There are time domain adaptive filters, non-linear adaptive filters, and there's also frequency domain adaptive filters. Even among these, there's many more types of adaptive filters than are listed here, but for today we will be going over 4 of each type. So I have created a mixture of a woman's voice and a man's voice, and I have added the room impulse response to give it the echo effect. And I have tried applying the filters of various adaptive filters on this recording. And first, let's hear the man's voice.
Hello, this is a recording for testing purposes. Thank you.
And now the woman's voice.
The wedding date has been set for Orlando in Florida in October. William Hague delighted his party. We played them off the pitch. Being captain of this club is fantastic.
And now the mixture.
The wedding date has been set for Orlando in Florida in October. William Hague delighted his party. We played them off the pitch.
Hello, this is a recording
Being
for
captain
testing
of this club
purposes.
is fantastic.
Thank you.
So first we have the time domain filters. And here's the first one.
The wedding date has been set for Orlando in Florida in October. William Hague delighted his party. We played them off the pitch.
Hello, this is a recording for testing purposes. Thank you.
The second one.
Hello, this is a recording for testing purposes. Thank you.
And the third one.
The wedding date.
Hello, this is a recording for testing purposes. Thank you.
And now we have the non-linear adaptive filters. Here's the first.
The wedding date has been set for Orlando in Florida in October. William Hague delighted his party. We played them off the pitch.
Hello, this is a recording for testing purposes. Thank you.
The wedding date has been set for Orlando
The second.
in October. William Hague delighted his party. We played them off the pitch.
Hello, this is a recording for testing purposes. Thank you.
And the third.
The wedding date has been set for Orlando in Florida in October. William Hague delighted his party. We played them off the pitch.
Hello, this is a recording for testing purposes. Thank you.
And this is the final.
The wedding date has been set for Orlando in Florida in October. William Hague delighted his party.
Hello, this is a recording for testing purposes. Thank you.
And now we have the frequency domain adaptive filters.
The wedding date has been set for Orlando in Florida in October. William Hague delighted his party. We played them off the pitch.
Hello, this is a recording for testing purposes. Thank you.
The second,
The wedding date has been set for Orlando in Florida in October. William Hague delighted his party. We played them off the pitch.
Hello, this is a recording
Being
for
captain
testing
of this
purposes.
club is
Thank you.
fantastic.
the third,
The wedding date has been set for Orlando in Florida in October. William Hague delighted his party. We played them off the pitch.
Hello, this is a recording for testing purposes. Thank you.
and the fourth.
The wedding date has been set for Orlando in Florida in October. William Hague delighted his party. We played them off the pitch.
Hello, this is a recording for testing purposes. Thank you.
So looking at all of these, you might have noticed a trend. For example, the time domain adaptive filters tend to perform better in separating the sound woman's voice before they mixed up with the man's voice, and the frequency domain adaptive filters, well, they clean up the mixed up part pretty well, while they still have a little bit of the woman's voice in the beginning, and somehow they even amplify the woman's voice in one of them. As for the non-linear adaptive filters, you can see that they don't quite seem to, well, filter out the noise almost entirely, one's voice almost entirely. However, well, while the non-linear adaptive filters are like that, there are other differences between the frequency domain adaptive filters and the time domain adaptive filters. So one of the differences is that the time domain adaptive filters are actually slower than the frequency domain adaptive filters when it comes to convergence speed. This is because the computational complexity of the frequency domain adaptive filters is reduced, is less than that of the time domain adaptive filters. However, the frequency domain adaptive filters have increased latency and memory requirement compared to the time domain adaptive filters. So if there are signals that have a really long echo path, it will require a lot of, it will have a lot of delay and memory requirements, so you would want to use a time domain adaptive filter or some other method than the frequency domain adaptive filter. However, none of these really seem to filter out the woman's voice entirely well, but we can check out different methods of creating and using adaptive filters. I believe that there are also deep learning methods that's used for this purpose, and also other ways to get the echo out of the system as well. Now moving on to sound source localization. So for sound source localization, I looked to the DCase 2021, where it looks for the third task is the sounds event localization and detection. with directional interference. So it's basically to find the direction in which this different sounds come from. This here is an architecture of the code I've tried implementing. It belongs to the team named the Nugan and I've chose this to implement this code because, well, they basically try to make a new feature for the purpose of sound source localization. Or they proposed a new feature for sound source localization called the spatial cue augmented log spectrogram, short for SARS, or shorted to SARSA, which has the exact time frequency mapping between the signal power and the source direction of signal, direction of arrival, and its code was also open code as well. Anyways, so these were basically trained on audio files that sounds something like this.
Set right line 6.
Spin blue at Z6 again.
Spin blue at D0.
Play blue by 30.
Well, if you are wearing headphones, you probably have heard how these sounds were coming from different directions, and this visualization over here actually shows the ground truth azimuth and the predicted azimuth using their program, their proposed method. And you can see that for most part they match up, while there are some places where there's some false positives and some mess ups. The large portions are actually pretty similar. And while this didn't place the first place in the leaderboard, their team did get to the 4th place overall. Or their submission, or in terms of the system, their submission was basically the 2nd team ranking. Anyways, so this table over here shows the submitted systems, and the ER stands for the error rate, and the F stands for the F1 score, and the LE stands for the localization error, and the LR stands for the localization recall, and the D cell stands for the metric for the low aggregated metric they use that's computed from different elements of the ER, F1, and LE, and R LR scores. So we basically want a low ER, high F, and low LE, and high LR, and a low decelled. And you can see that when I implemented it, I got the following score, which is significantly worse than the ones that their team submitted to the DKs. But this is because I did not have the time to train the whole data set that these people trained, nor did I have the time to train them for as many epochs because of time constraint. However, I believe this actually shows the superiority of this pretty well, even as it is, because while these scores seem much worse than the are much worse than the originals, they actually compete pretty fairly on the leaderboard for DK's 2021, in that the error rate of the DK's 2021's fifth place was 0.46 compared to the 0.42 here, and the F1 score was 0.6 or 67.8 compared to the 69.7 over here, and the localization error was 12.8 compared to the 11.722. And for the localization error, it's actually higher than the third places, even with this. And for the localization recall, that's where it kind of fails compared to the others, but that's also 687, which basically places seventh place in the leaderboard for DK's 2021. So yes, even in incomplete training managed to get it into top 6 for all of the scores. By the way, the decelled score wasn't in the leaderboard, it's a score made by the team that created this feature. Anyways, the reason I chose to use this was because since it's a feature, I believe that it could be combined with the different neural networks in order to create a better, more accurate sound source localization method. Now we are on to speaker diarization. So for speaker diarization, there's actually a lot of frameworks open to public. These include PianoNote, NVIDIA Nemo, Simple Diary, and SpeechBrain, and CowD. However, I focused on PianoNote because that's basically the top in this in this in this field of study. So with using piano's pre-trained model, we can it has an error rate of 19.2%, and it's trained on sounds like this. Oh, this is actually too long, so I'll just skip ahead.
Birds of prey, aren't they? Oh dear. Intrepid. Intrepid.
Well, I kind of forgot to explain the concept of speaker derivation again, but speaker derivation is basically answering the question of said who spoke when. So in the recording you just heard, there were some persons speaking and someone giggled, kind of laughed in the middle, so that should also show in the speaker derivation. But this recording was too long, so over here we only have a portion of it. By the way, this is seconds, not milliseconds, so it's like 600 seconds to 60 seconds, a whole minute. Anyways, this over here on top is it's predicted Diarization, and this on the bottom is the ground truth Diarization. And you can see that there are several errors in the place, despite this being pre-trained. Small errors, but there's still errors. And I tried using my own data, and this is the sound.
The wedding date has been set for Orlando in Florida in October. William Hague delighted his party. We played them off the pitch.
Hello, this is a recording
Being
for
captain
testing
of this club
purposes.
is fantastic.
Thank you.
A pencil with black lead writes best. The lamp shone with a steady green flame.
So you can see that, well, this on top is the predicted Diarization, the result output from the Diarization, and this on bottom is the ground truth. And you can see that it misinterprets this portion as speaker number 2, despite this speaker number 1 speaking all the way up to here. And speaker number 1 over actually starts speaking after both speaker number 1 and speaker number 2 has finished, but this doesn't reflect that. And while I'd like to say there's some miraculous way to improve this significantly, I believe there's only fine-tuning that I can do, because currently piano note is the top of the technology in the speaker derivation in terms of open sources, and we can only really use more data to train it and fine-tune it to improve its quality. And this is really difficult to do because this requires lots of labeling, lots of strongly labeled data. So in conclusion, I believe that for the future I want to use deep learning to remove the echo from the sounds rather than just the traditional acoustic echo cancellation methods, And I'd like to also try combining the method I tried today with methods that other methods that use different types of neural networks, because I believe that this will be more useful, as one of the one I used today for this presentation basically uses a new feature, and features can be really applied to any neural networks. So combining it with a different neural network may provide a better result for on-source localization. And for the speaker diarization, Piano is one of the best speaker diarization codes to date. Even this year they've placed #1 in 2 different contest places, I believe, and they would be able to perform better if they were fine-tuned on some new data or original data. Thank you.